Hello everyone and welcome back to another YouTube video. This time I'm going to be talking about gravitation, and this is something that I've thought about for quite a few years now, and I think I'm really starting to get some good insights on this, so I wanted to share these here. One of the confusing things that if you ever read a popular science textbook on general relativity or really anything physics related, it can be extremely confusing because they're only talking to you in terms of language. So, for example, I don't know if you've ever heard of this concept of space-time, but there's this whole thing that all these physicists come on and they're like, wow, before Einstein, space and time were two different things. And then now it's space-time. They're the same thing. And you're like, wow, that sounds kind of cool, but it just kind of sounds like you combined two words into one word and called it space-time. So I really want to talk about that and actually make it very clear as to what that actually means mathematically, because it's a lot clearer. Mathematics is extremely clear. It's not very ambiguous as to what it means most of the time. And so I'm going to talk about that. First, before I do that, just a brief history of gravitation. So gravitation, the study of it, started with Galileo. Galileo used to do experiments of dropping things from the Leaning Tower of Pisa, and he did some other experiments at home. And he didn't have very sophisticated mathematics, so even what we learn today in elementary school with algebra, he didn't really have access to that kind of mathematics at the time. It wasn't really around. So what Galileo did is when he did an experiment, he would say quantity A, some number, is related to another quantity B in some way. So, for example, in everyday life, generally speaking, how fast you get somewhere, it depends on how far it is, but it also depends on how fast you're going. So, generally speaking, the distance that you have to travel or the time it takes to travel that distance will go down as the faster you go. And these kinds of proportionality things are everywhere in physics. But usually in physics, you'll take a proportionality thing and then you'll shift it into a more algebraic thing like F equals ma or something like that. So Galileo, he got decently far, but to be honest, he didn't have the mathematical tools at the time to make a general theory about what he was describing. But he really is kind of the founder of investigating the natural world as it is and not philosophizing about it. This might seem very foreign to a lot of us because we did not grow up in schools where when you're doing science class, you're just sitting there just thinking about things. That's kind of what people used to do, and Galileo was the first one to kind of stop just thinking about things and actually start doing experiments. Isaac Newton, he was the one who really kick-started the proper mathematical formulation of gravitational theory. So he's famous for F equals ma and his three laws. But his gravitational theory looks like this. So it's the force of gravity is equal to some constant times the mass of the first object, mass of the second object, and then this is the radius squared. So what you're going to do is if I have mass 1 here, and I mass 2 here. You draw a circle. This is a really bad circle. And then you basically will measure this radius and then take whatever number that is and square it and then shove it down here. And you can calculate this for a lot of things. It's kind of fun. One thing I should mention though is this g here. So in physics, there's a lot of these constants that appear. And if you've ever been confused why they're all there, it's because in physics, they actually care about the units of measurement. So you can't just arbitrarily, um, have numbers in there doing whatever they want. They actually have to have some physical meaning. This is very counter. Like I had issues with this because in math, it's not really about. We don't measure things. So, for example, if you're solving this equation, for both the x values that make it 0, all you need to know is that the x's are numbers. Uh, you don't need to know that they're measured in meters or that they're measured in kilometers per second or any of that stuff. Whereas in physics, you do have to make sure that that's the case. And so basically, what happens is, well, Newton's like, I have a mass here. This is in kilograms or something. This is in kilograms. And this is a distance. So how am I going to get all the units to kind of work out into something that we want to measure? And this is where this g comes from. which it's kind of a conversion factor if you want to think about it that way. It's kind of like when you're converting between currencies a little bit, you need to know the exchange rates. And this will give you a force of gravity measured in something called a Newton, which was named after him. I think I forget what the exact measurement units were, but not important. So as you can see, though, Newton wrote down a mathematical formulation. So he actually gave us a way of calculating what the force of gravity between two objects is anywhere in the universe. A few things that came out of this. One thing you'll notice is that this doesn't actually prevent you from looking at the force of gravity between objects that are three, 3 light years away and 3 meters away. There's no distinction being made between exactly what objects are attracting what. And this was kind of one of the interesting things. They thought that this was nonsense. Actually, even Newton, I think I mentioned previously, he thought this was nonsense because you could apply this to another galaxy. You can measure the force between you and another galaxy. You can also measure the force between you and the center of our galaxy, which is a black hole. And the attraction you get will probably be very small. I don't think it'll be very small actually if you're doing a black hole. But this idea that, some object that's very, very, very far away has this kind of immediate, attractive force to you wherever you're going, whether you're going to the grocery store or you're going to play soccer or something, it's a little ridiculous. So they knew there was something wrong with it, but it really took until Einstein to figure this out. Now, Einstein is very different. What I want to say here is as you go left to right, the increase in mathematical sophistication is exponential. Galileo's approach was very numerics based. There wasn't a lot of algebra. Newton was more algebraic, something called a differential equation. You can solve it. It's a bit more complicated, but still very manageable. Einstein's equation is just an absolute mess. Einstein uses a branch of mathematics called tensor calculus. Tensor calculus. And this is basically a generalization of vector calculus. So if you did any line integrals, path integrals in school, this is basically a generalization of even that. So if you did not like that, you're most certainly not going to like tensor calculus. One of the main reasons that tensor calculus was needed is because he needed a mathematical language to represent his theory in. And fundamental to this was this thing called the principle of equivalence, which is really what started to drive the idea of um, of Einstein thinking that space and time are one and the same. So that's actually what I want to talk about right now. What was Einstein's big idea, and why do they keep calling it space-time? I was going to use this previously, but whatever. Actually, I can say something about this. So one of Galileo's approaches was he would take a ball like a ball like this one here, and he would just kind of watch it going over a table. So this is a table. He would watch the ball rolling over a table, and he would notice that the component of force going this way was giving out to the force going down. So eventually, this object gets pulled to the ground. And so he didn't know exactly how to write this out mathematically, but he kind of had an intuitive idea of what was happening. That's kind of what I was mentioning. Okay, so what is space-time? And what does this stuff mean? So to illustrate this, Newton's equations, Newton's equations are stuff like F equals ma, okay? So let me write these forces out. So F equals ma, and I'm going to explicitly write these, actually let me write these out in a different way. So there's something called the displacement, which is a function of time, okay? And then you take the first derivative of this, and this is called the velocity because it's how much you're changing your position, so how fast you're going. And then if you change your position very quickly, if you're changing the change, then if you're changing the rate at which you're changing, then we call this acceleration. So this is acceleration, okay? And basically acceleration is then, using this fancy notation here, the second derivative of this displacement. This is what second derivative is. So F equals ma can be rewritten as the force is equal to the mass times the acceleration. So very simply, if you're not accelerating, then there's no force because this term just becomes zero, it just goes away. If you Similarly, if you have a constant velocity, this is also zero because the derivative of a constant uh, is zero as well. And anyway, so let's talk about this. So this is F equals ma, and then we also have the force of gravity. So gravity is a Newton times mass one, mass two, or r squared. And basically, in Newton's world, which you might be able to see from here, from what I've written here, um, all of these quantities, so your acceleration, your velocity, although this is happening in three dimensions, which I can draw right now, like this. So let me draw this out. So here we have three axes. So let me draw this out. X, Y. Don't worry if you've never seen this. Three dimensions is actually very intuitive to most of us, not all of us. And basically, imagine you're on a plane or something, and you're flying around and you're doing stuff, and all is very well. So you're going from point A down here to point B up here. So in Newton's world, first of all, the world is only three dimensions. And the reason that it's three dimensions is because in Newton's equations, the way that you specify that you're in three dimensions is you basically say that each of uh, these number lines here, so the x number line here, the y number line here, and the z number line here, all of these depend on time. What does that mean? Mathematically, it's very, very simple actually to write this down. We just say that x depends on time. That's what this means. Y depends on time. The z coordinate depends on time. And you can stack these up and you can call this a vector if you want. And basically what's happening in Newton's equations is that you're going to measure this force quantity here for each one of your coordinates here. So each one of the things you have to keep track of. Because as you move on the number line, like for example, if I start here and then I move over here, on this number line, maybe I start here and then I move down here. That was bad. And then if on the Z I start up here and then I move down here or something, then I need to keep track of the fact that I'm moving around, kind of sliding around on each part of these number lines. And so I need to make sure that I'm keeping track of that. So I think we would be somewhere over here. It's hard to draw this, but the point we would have been at is like up here somewhere. I can't really draw 3D, but anyway, the main idea is that each coordinate, each time you're moving around, you're sliding around on these three axes, it all depends on time. And we actually assume that this happens. We're assuming that each of these coordinates, as we call them in mathematics, each of these coordinates depends explicitly on time. You can see that I've written time here. Okay, so this is Newton's version. Einstein realized, well, this is not correct. And he made the ingenious step. Let me show you. Einstein's world, Einstein's world, Einstein's equation. Einstein made the leap and said, it should not be like this, where each coordinate depends on time. No, this is wrong. It should actually be this. You have x, y, z, and t. So basically what Einstein did is he took the time variable that all these things in Newton's world were depending on and just made it its own variable. So uh, you basically can think about time as being like any of these other ones. Heck, you could even, if you really wanted to, you could rename these x1, x2, x3, x4 if you're a mathematician or something. But because we're in the physics land and we care about units and we care about the meaning of things, you still need to call this time. So why is this so important? Well, now that you can see that when time moves over here, So if I start shifting time around, it doesn't impact or doesn't have to impact the other variables that enter the equation. It means that time can go on and I'm not necessarily moving around anywhere. Over in Newton's land, if I move these variables along, these functions, unless they're exactly constant, they're just exactly constant functions and you're not going anywhere, or they're all zero, you necessarily have to be moving. And so in time, we assume that, basically things are moving, things depend on time, and it's a very different kind of picture that you can paint. So Einstein's world is extremely complicated. Um, the main reason for this is the fact that it's not really the fact that it's now four dimensions, meaning you have four axes that you can work with, four different things that you can vary. That's not really the difficulty. The difficulty is now that um, in doing experiments in general relativity, actually getting quantifiable predictions out can be very challenging. So there's two versions. One is called special relativity, and another one is called general relativity. Okay. So what we can do here is, let me see if I can pull up the equation. Yes. Okay, here it is. So in special relativity, what you can do is everything is flat. So we assume that just kind of like how I drew previously, we have these three axes that all meet at right um, right angles to one another. Instead of this, imagine just a four-dimensional thing. So same principle, it's just that we can't really draw it. In general relativity, what makes it so dang hard is that instead of just having straight lines connecting and basically measuring everything from the perspective of these four straight lines, it actually has this ability to take straight lines and then describe them using curved lines, like something like this. Okay? So instead of having, here, let me draw this a bit better. Again, this is only three dimensions. But basically, instead of having just, here's my X, here's my Y, here's my Z, you can actually change these three solid bars into three squiggly bars that are actually functions themselves. And then you can start to measure things just like you would have over here. If I have a point over here, I can say like, oh, it's 4 units over here, 5 units this way, and 6 units up. And I can draw a line from there to there, bing, bada, boom. Similarly, here you can do the same thing. However, it's continuous. It allows for something called curvature. So, and if I want to follow this axis, usually I would just draw a straight line above, but now I have to curve. I have to curve, I have to curve, and I pass through this point, okay? So it's very, very different. And this is where all the difficulty comes in general relativity. The fact that maybe you've heard that gravity can distort space-time. What this really means is that if you have a really heavy object, such as the sun, like really, really massive, or a black hole, if you have a really, really big object, what this does to gravity is that suppose we have G, gravity just goes way up. The strength of your attraction just grows up quite a bit. And not even that. We imagine that basically the Earth is kind of bending this space-time thing. And what does that actually mean? So what it means is, let me see if I can draw it. This is very poor. I don't even know what I'm trying to draw here. What it means is that the the way things move around the sun and the way things move around these massive objects, they have to curve. So they don't just go straight, they curve around it like this. Okay? So if I'm my light beam number one and I'm light beam number two, when I go really close to the sun kind of pulls me in. And if you ever use those coin machines at the Toronto Zoo where you flick a coin in and then there's a bowl, and then in the bowl, the coins kind of go down through this series of things into the center, and then your coin goes into this hole and slot, and you've donated some money. It's the same idea. I just haven't drawn all the lines here to really indicate this, but basically the actual way that things move around these objects is distorted. Okay? So this is very hard to understand and really quite hard to wrap your mind around. And the level of mathematics greatly, greatly, greatly increases. So let me write down the equation of special relativity, which can really be defined as this. So the distances between two events, meaning occurrences in space, there's a more philosophically correct version of this um, that I'm not going to use. We take the change in the time, and we take the change in x plus the change in y plus the change in z. So there's a lot of other things baked into here, but basically, if we want to measure the interval of time or some kind of quantity of interest between two events in space, then we can use special relativity, which is assuming that everything is flat, meaning in our local vicinity, the force of gravity is not important. So even on the Earth, suppose that you're only considering like think about, for example, in your own office or in your own bedroom. So your bed is probably very flat. If you took a what is that thing called? If you try to measure how flat it exactly was, it'd probably be almost exactly flat. Okay. Now imagine you had, instead of a bed that was maybe 8 feet long, it's now 100,000 feet long. Okay. And maybe what you can think about is if you took some object and then you really like stretch it out that has some mass to it. Like if you try to make a really, really, really long table, you'll notice that eventually there's going to be points in that table or in this really big bed you now have, they're going to be curving down, that they're getting weighed down on. And this is exactly gravity happening. And so that is, in some sense, the idea here. If you're operating in a very small area of space, you can use special relativity, which is basically going to give you the correction that you need to make to Newton's theory to get the most accurate results. General relativity is really for very extremely large objects. And the equation of general relativity looks like something that, you know, it looks scary, and it is scary. And I've been trying to understand this equation for a number of years now. Uh, and it's very formidable. This is very not very user friendly. So what is this stuff meaning? So if you took any linear algebra, these things are called indexes. And basically what this is this equation is a 4 by 4 matrix of partial differential equations that are going to tell you what the geodesics are. So what are geodesics? It's going to tell you that, if you have something like the sun, how does light bend around the sun? What angle is it supposed to make? Um, One of the first actual experiments in general relativity was there was a solar eclipse, and basically this during World War One, this guy had found a way to get down into this area where it was going to have basically a direct on shot of the solar eclipse. And so the moon, let me see if I can draw this. When the moon covers okay, this is not going to work. So when the moon covers the sun, what happened is um, you could see around the moon all of the different light kind of spinning around it. Sorry, not spinning around it, coming around it. And so what this guy did, Arthur Eddington, is he measured these solar, light rays, and was able to determine this the angle predicted by general relativity for these beams of light going around something like the mass of the sun was very, very accurate. And this was a very interesting prediction of general relativity. Before, people used to work with just flat spacetimes. Or sorry, not flat spacetimes. They used to work with only flat coordinate systems, where you have, three coordinates, and uh, basically they're all at right angles to one another. Instead of doing this, you can do a more general thing, which is allowing them to not necessarily be 90 degrees, but you can use different kind of ideas of orthogonality. Orthogonality. So anyway, this is general relativity. Now, for all intents and purposes, you don't need to use general relativity unless you're doing black hole physics or you're doing anything with regards to the universe. That's another thing. So if you're trying to figure out things like singularities, those kinds of things, you need to use general relativity because it's the most accurate in terms of the dynamics of the entire universe. Whereas Newton's equation is not sufficient for that, and neither is special relativity because uh, this assumes a totally globally flat, what is called a manifold. I won't go into that, but um, yeah, so basically, the level of mathematical sophistication since Galileo first identified that there might be something called gravity that exists to now, where Einstein, about 100 years ago, was the one who came up with just general relativity equation, which is 16 partial differential equations that describe how things move around massive objects. It's very interesting, very, very, very interesting stuff. Uh, Personally, I really realized this, kind of slight uh, kind of magic that was going on with the space-time stuff only recently. Because I noticed, I'm like, man, when you solve Newton's equation, you're always solving it with things that depend on time. Because in mathematics, you learn there's these things called parametric equations, okay? Which means that if you wanted to write every dynamical system, meaning things that move like you and myself, you can write them in terms of one parameter. And then you can move that one parameter back and forth and back and forth. And that's what they were doing. You would use everything as time would be kind of baked into your understanding. And then Einstein came along and said, no, 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 no. Time is not something that you should be, the space of where you're moving things should not depend on time explicitly. It should actually be treated as its own kind of thing. And it should actually form a four vector. So very, very interesting stuff. Very, very cool. In the future, I'm going to be talking about string theory and why people are looking for this kind of thing called a grand unified theory. Why are they looking at string theory? What is it? What is its importance? Why is it interesting? And I might also talk about some of Stephen Hawking's work. I don't fully understand a lot of it, but I can try in my very best and kind of use my own way of understanding things to explain it in much simpler terms than what goes on in a lot of these research papers where they're doing kind of cutting edge mathematics or interpretation of mathematics in physics. So very, very cool. If you made it this far, congratulations, and I hope to uh, upload soon. Thank you very much. Bye bye.